we're going to talk about single replacement reactions in this lesson, part of the types of reactions series. So to get started, we're going to simply define a single replacement reaction. It is when there is a chemical change in which one element replaces a second element in a compound. So we have a compound, and then an element comes in, cuts in place for one of the other ones, and kicks it out. And we can show that with this drawing here. So we start out with AB, and we are going to react that with element C. And what happens is C will actually take the place of A. It could also take the place of B depending on what type of element C is. So you can also see this with the colored dots. We start with the blue and the yellow circle bonded. The green circle takes the place of the blue circle, and we are left with a new compound as well as a new element on its own. You can kind of think of this if there are two people at a dancing, and then a third person comes and cuts in and starts dancing with one of those people in the couple, or that were previously in the couple. That is a single replacement reaction. All right, so again, here is an example. We have A plus BX yields B plus AX. So again, a single element coming in and replacing an element found in a compound. It can be either a cation that is replaced, as you see in the middle example where it says cation replacement. Zinc reacts with copper 2 chloride to form zinc chloride and then solid copper. Or an anion can be replaced where we have bromine reacting with potassium iodide to yield potassium bromide plus elemental iodine. Okay, so in the first sample, the cation is being replaced. Copper is replaced with zinc. And in the second example, the anion, iodide, is replaced with bromine. So it can be either or depending upon the circumstances. Single replacement reactions don't always take place. If you have ever worn jewelry like gold or silver, when swimming in the ocean, we would be a little bit concerned, right? Because there is salt in the ocean, sodium chloride. And we would not want a single replacement reaction to happen at that point in time because we wouldn't want the gold or silver from your jewelry replacing the sodium, where you would end up with a sodium ring or necklace or earrings. So we need to learn how to tell when a single replacement reaction takes place. The element that starts out on its own, so the element doing the replacing, needs to be more reactive than the element that is already in the compound. Okay, so if we go back to the analogy of the dancers, the person who's cutting in, for them to be accepted by one of the people already dancing, they need to be extremely charming. Otherwise, if they weren't charming enough, the dancers wouldn't let them into the group and you cut in. Okay, so we've got two lists here. We have a list of metals or things that typically form cations on your left, and then things that typically form anions, which is also the halogen series, on the right. These are going to be very useful. Okay, we can see that on the top for both of them are the most reactive elements. Okay, those are the elements that are going to be more likely to cause a single replacement reaction to take place if they are on their own. An important note on the left-hand chart about hydrogen. Potassium, sodium, and calcium. Those three are so reactive that they will actually replace hydrogen in water. So if we put those solid metals into water, it will react with the water, replacing the hydrogen. Hydrogen is listed on this chart just beneath lead because that's how reactive it is, or everything above it will replace a hydrogen when the hydrogen is in an acid. So everything above that will react with an acid to cause a single replacement reaction. All right, let's take a look at an example problem. So we have solid potassium and water, H2O, a molecular compound. We need to predict what's going to happen here. So potassium is going to form a positive ion and replace one of the hydrogen in the water. So we go with the potassium taking the place of one of the hydrogen in the water, and we get KOH, which is potassium hydroxide. The leftover component is hydrogen, so we need to add hydrogen in. Of course, hydrogen won't ever be just by itself, so we need to make sure that we represent it as diatomic here. Now, we need to look at this equation and see if it's balanced. We can see that there are 3 hydrogen on the right-hand side and only 2 on the left, so we know that it's not balanced. So with a little bit of work here, I think we are taken care of. So again, we saw that potassium is reactive enough to replace one of the hydrogens in water, and then we just moved it in. We paired it with the anion hydroxide, and then figured out what the rest of the products would be. I'm going to give you a practice problem here where we have silver nitrate reacting with solid zinc. I've included the reactivity chart on the lower right hand corner of this slide, so you can attempt to do this problem. I recommend pausing the video, trying it, and unpausing it when you are ready to see the solution. Okay, you must be ready for the solution. So we are going to look on our activity series here on the chart on the lower right hand corner, and we are going to see, is zinc more reactive than silver? Zinc forms a cation, so it would replace the silver in silver nitrate. If we look at our chart, silver is near the bottom of reactivity. It is not a very reactive element, whereas zinc is right in the middle, even a little closer to the top. So zinc certainly could replace silver in this equation. So we take zinc and remove silver and pair up nitrate with zinc. Now zinc forms a positive 2 charge, so we need 2 nitrates to write the correct formula, and it is aqueous, so we have zinc nitrate. The silver is what is left over when we are done with this. So we add solid silver. Simply just taking the atom or element that had been replaced and putting it as its own portion of the equation. Now we need to balance it, which you have become adept at, and so we just need a couple of 2's to get it to work out. Okay, we have a second practice problem. We have sodium chloride in solution and we add solid iodine. I recommend that you pause the video and give this problem a shot. Okay, you're back and hopefully figured out that I was trying to trick you a little bit. If we look at the reactivity series for halogens in the lower right hand corner, we can see that chlorine is the second most reactive of the halogens. The only one more reactive is fluorine. So fluorine is the only halogen that could replace chlorine in this compound. Iodine is at the bottom. Iodine, when talking about halogens, is not very reactive. So all we would need to write for this problem is no reaction. Remember, if the lone element is less reactive than whatever it's trying to replace, it can't do it. There will simply be no reaction. Okay. Here's all our final information. I've given you the general equation. We have T plus Rs yields Ts plus R. And I want to point out that uh, remember, both the cation or the anion could be replaced. So you need to pay attention to what would be doing the replacing, and does it typically make a positive or negative charge. For reactants, you should always start with a compound and an element, and that element needs to be more reactive than whatever it's replacing. The probable products will be a new compound and then a new element. As always, check the comments on YouTube to see where you can find more practice problems in your book.